Huh. Hello everyone, very good evening. Kindly confirm if audio video is clear. Okay, all fine. Thank you very much. So guys, let's begin with the next session of set theory and algebra. This will be the fifth lecture of set theory and algebra in this particular series. So, what have we already discussed in the last class? So in the last class, that is yesterday, I discussed the concept of equivalence class. What is equivalence class? So equivalence class is defined for the elements of a set A with respect to an equivalence relation, right? So equivalence class of an element X will be nothing but the set of all element Y such that element X relates with element Y with respect to equivalence relation R. So that we have already discussed. Next, partition. So last two classes we are discussing the concept of partition. The last class we discussed the number of partition of a given set of a given particular cardinality. Apart from that, we could identify that the set of distinct equivalence classes will create a partition of a set. That's what we discussed. Then we said that there will be one-to-one correspondence between partition of a set and equivalence relation on that particular set. So basically, number of equivalence relation on set A will be exactly same as number of partitions of set A. So that we discussed. Then we started with the concept of partial order relation. So what is a partial order relation? So we'll discuss that again in a while. But today we are going to discuss about least upper bound and greatest lower bound of a partially ordered set, and then we'll discuss about Hasse diagram. So today's topic will be Hasse diagram. But in the Hasse diagram, we'll also try to see the least upper bound and greatest lower bound for a pair of element of the poset. Therefore, these two things will be discussed simultaneously. Okay, so let's have a quick revision for the from the last class for partial order relation. So what is a partial order relation? Sir, a relation R is called a partial order relation if it is reflexive, antisymmetric and transitive. If these three properties are satisfied, then the relation will be called partial order relation. I said that diagonal relation on set A will be smallest partial order relation, and it is the only relation which is partial order relation as well as equivalence relation. Okay, next, so that we have already seen. So let's try to understand. I give you this as an example. So what we need to see whenever we are looking at a partial order relation, it should be reflexive. Yes, all diagonal order pairs with respect to set A are present. It should be antisymmetric. 1, 2 is present, so 2, 1 should not be present. 2, 3 is present, so 3, 2 should not be present. Apart from that, it should be transitive. So 1 to 2 and 2 to 3, 1 to 2 and 2 to 3. Therefore, 1, 3 should also be present. So all these three properties, reflexive, antisymmetric and transitivity properties must be satisfied. Okay. Then what did we say? What is a partial ordered set? Set along with the partial order relation will be called partially ordered set. So I gave some example that relation less than equals to on any set of real numbers will be a partial order relation. If you take any set and if you try to define all the order pairs with respect to relation less than equals to, then you will identify that the order pairs in the relation less than equals to will satisfy all three properties. It will be reflexive, it will be antisymmetric only from only from upper triangular or lower triangle the elements are present, so it will be antisymmetric obviously, and it is transitive. 1 to 2 and 2 to 3, therefore 1 to 3 is also present. Similarly, 1 to 2 and 2 to 4, so 1 to 4 is also present, etc. So apart from that, it's not only with respect to less than equals to, but we can define the partial order relation with respect to some other relations also. So it's something but that you will eventually learn with the question, that the relation may be less than equals to, the relation may be division or divides, basically the relation may be subset or equals to, there may be any relation. We will try to see each and every type of example. So if A is any set of positive integers, then I said if A is any set of positive integers, then if you look at the order pairs with respect to relation divides, then it will also be a partial order relation. So this is your example 1, 2, 3, 4. So This is reflexive because every element divides itself. Apart from that, if x divides y and y divides z, therefore x will also divide z, therefore it will be transitive also. Now, a smaller number can divide larger number if at all division is possible. So, a smaller number will divide larger number, but larger number can never divide smaller number, so it will be antisymmetric also, right? So, this on any set of positive integer, relation divide will be partial order relation. Here also the same example, but after that, I also defined the definition of comparability, that two elements are said to be comparable. In what case? If either A relates to B or B relates to A in the partial order relation R, then A and B are said to be comparable. So that's what we have also seen, that if you look at this, neither 2 divides 3 nor 3 divides 2, neither 2 divides 3 nor 3 divides 2, therefore 2 and 3 are not comparable. Similarly, neither 3 divides 4 nor 4 divides 3, therefore 3 and 4 are also not comparable. So in a poset, it is not necessary that all the pair of elements of the set will be comparable. But if it happens that all the pair of elements are comparable with respect to given relation, then that relation will be called total order relation. So what is a total order relation? A partial order in which all the pair of elements, that is every pair of elements of set are comparable with respect to equivalence relation, then that particular relation will be called total order relation. Clear? So yes, let's look at this. There are some pair of elements which are not comparable with respect to relation divide. Therefore, this poset is not a total order relation. But in this case, all pair of elements of set A are comparable with respect to relation divide. So in this case, this divide is a total order relation. Now, both of them are actually posets. So if I try to define the totally ordered set, then what is a totally ordered set? Sir, a poset, obviously, before it becomes a total order relation, it will be a partial order relation. So, a poset in which all the pair of elements of set A are comparable with each other, that is, the respective relation is a total order relation, then it will be called a totally ordered set. So, this is from the last class. Let's look at the today's session. Oh, so very first thing that we'll discuss is the least upper bound. So, the least upper bound is also known as, so generally we denote it using least upper bound. The symbol that we use is this symbol like OR symbol. Apart from that, least upper bound is also known as join, and this least upper bound is also known as supremum. So there are various names given to the, all of them are same thing, whether it is least upper bound, join, supremum, whatever, all of them are same. Now please try to understand. What do we know? We are defining least upper bound or greatest lower bound in context of a poset, partially ordered set. So let's try to understand the definition first. So it will be very easy to understand in terms of less than equals to, therefore I am trying to define it with respect to less than equals to, but I can generalize it for any relation R. Let me first copy this. Well, with other relation also. Okay. So let's assume that A with respect to relation less than equals to is a partially ordered set. For any two elements A comma B belonging to set A, if you have two elements A and B from set A, they need not be distinct, they may be same also. If you have any pair of element A and B belonging to set A, and if there exists any element C belonging to set A, if there exists any element C belonging to set A such that C is at the upper side of A as well as at the upper side of B. What are we looking at? Sir, we are looking at upper bound. We are looking at upper bound. So the elements which are on the upper side of both these elements A and B will be called upper bound of A and B. Will be called upper bound of A and B. So if there is any element C which is on the upper side of A as well as on the upper side of B, then we will say that C is called upper bound of A and B. But are we interested in the random upper bound? No, sir. We are interested in the least of all the possible upper bounds. We are interested in least of all the possible upper bounds of these elements A and B. So, okay, we have understood the concept of upper bound, but now we are interested in the least upper bound. Please look at this. So this is okay that if there exists an element C which is on the upper side of A as well as on the upper side of B, then it will be called upper bound of A and B. But if there exists no element, if there does not exist any element D belonging to set A, if there does not exist any element D belonging to set A such that D is on the upper side of A and B, that is D is the upper bound of A and B and D is at the lower side of C. If there does not exist any element D, if we do not have any element D in the set A, if we do not have any element D in the set A such that D is also on the upper side but it is on the lower side of C, then what does it mean? Then we are actually trying to say that there is no upper bound of A and B, because this is the definition of upper bound. So we are actually trying to say that there is no upper bound of A and B which is at the lower side of C. That is, there is no upper bound of A and B which is smaller than C. Then in that case, we already know that C is the upper bound, but if there is no other upper bound of A and B which is at the lower side of C, then C will eventually become least of all the upper bounds. Then C will eventually become least of all the upper bounds. So if C is an upper bound of A and B and there is no other bound of A, there is no other upper bound of A and B which is at the lower side of C, then C will become least of all the upper bounds. Make sense? So this is the simple definition. Okay, so I'll give you an example, don't worry about that. But I tried to explain the concept in terms of less than equals to, because it is very easy to visualize that yes, C is on the upper side of A and B. But what actually will be the scenario for a random relation R? So let's assume that this is any partial order relation R. So you just need to understand that in this partial order relation R, if A or if X comma Y belongs to relation R, if X comma Y belongs to relation R, then please try to understand that if it is, let's visualize in terms of less than equals to. So if I say 2 comma 3 belongs to less than equals to 2 comma 3 belongs to less than equals to, when exactly it will happen? When 2 is less than or equals to 3, then only 2 comma 3 will belong to relation less than equals to. Is it possible that 3 comma 2 belongs to less than equals to? No sir, 3 comma 2 will not belong to less than equals to, because 3 is not on the lower side of 2 with respect to relation less than equals to. So you simply need to understand that if X comma Y belong to relation R, then this X is at the lower side and this Y is considered at upper side. So for any random relation R, if there is an order pair X comma Y belonging to R, then we say that X is at the lower side with respect to Y and Y is at the upper side with respect to X. Clear? So that's the simple concept. Now, if we have any random relation R, then two elements A comma B belonging to set A. Then for two elements A comma B belonging to set A, if we have any element C belonging to set A such that, forget about this, if I say that A relates to C and B relates to C, that is, so what does it mean? That is A comma C belong to R and B comma C belong to R, that is C. What did I say? If in X comma Y is at the upper side. So if we are saying that A comma C belong to R, that is C is at the upper side, and B comma C belong to R, that is C is at the upper side with respect to B. In this case, C is at the upper side with respect to A. So if C is at the upper side of both A and B, then C will be called upper bound of A and B. Exact same concept. Then C is called upper bound of A and B. So it need not be with respect to less than or equals to, it can be with respect to any random partial order relation R. Clear? So that's okay. Now, if there exists no element D, if there exists no element D belonging to set A such that, forget about this, such that, what should be the condition? Such that A relates to D and B relates to D. That is, if there exists no element D which is upper bound of A and B, and that D is at the lower side of C, and that D is at the lower side of C, then there is no other upper bound of A and B which is at the lower side of C. That means C is actually the least of all the upper bounds of A and B. C is actually the least of all the upper bounds of A and B. We are not saying that there is no other upper bound of A and B, but we are simply saying that there is no other upper bound of A and B which is at the lower side of C. Then in that case, C will become least of all the upper bounds. Clear? Oh, so I'll give you an example for least upper bound and least upper bound in a while, but first of all, let us understand the concept of greatest lower bound. So it is exactly same as least upper bound. So what are we saying, sir? Again, if we say 2, 3 belongs to less than equals to, then, right, then this is at the lower side and this is at the upper side. So in the previous case, we were looking at the upper bound. This time we are looking at the lower bound. So if we are looking for the lower bounds of A and B, then we are looking for the element C which are on the lower side of A as well as on the lower side of B. So in the upper bound, we are looking for the elements which are on the upper side of A as well as on the upper side of B. So for lower bound, we'll look for the element C. We'll look for the element C which are on the lower side of A as well as on. Clear? So that's the idea. So for the same poset A with respect to relation less than equals to, if there exists two elements A and B in set A, and if there exists an element C belonging to set A such that C is at the lower side of A as well as at the lower side of B, then C will be called lower bound of A and B. C will be called lower bound of A and B. But again, we are not interested in a random lower bound. We are interested in the greatest of all the lower bounds of A and B. So, if there does not exist any element D, if there does not exist any element D such that D is at the lower bound of A and B, but D is at the upper side of C, then D will if there does not exist any element, if there does not exist any element D belonging to set A such that D is at the lower side of A and B and D is at the upper side of C, then there will be no other lower bound D of A and B which is greater than C. Then C will become greatest of all the lower bounds. Then C will become greatest of all the lower bounds. That is, C will become greatest lower bound of A and B. Clear? This is as simple as that. So, in the very beginning, it may look confusing, but it's so simple. You just need to understand that in x comma y, if we have x comma y belonging to R, then we consider x at the lower side and we consider y at the upper side. That's the simple concept. Now I can generalize this in terms of relation R. So that okay. So let's assume at the place of less than equals to, if we have any random relation R. So let's assume A comma R is a poset for two elements A comma B belonging to set A. If there exists an element C belonging to set A such that, if there exists an element C belonging to set A such that C is at the lower side of A and C is at the lower side of B with respect to relation R, then C is called lower bound of A and B. Then C is called lower bound of A and B. And if there exists no element, D belonging to set A, if there is no element D belonging to set A such that D is at the lower side of A and D at the lower side of B, that is if there exists no element D which is lower bound of A and B, and D is at the upper side of C, then ultimately there is no lower bound of A and B which is at the upper side of C. That means C is the greatest of all the lower bounds. Then C is called greatest lower bound of A. Anyway, I'll just give you an example. You will understand that. So let's take an example. 1, 2, 3, 4. Let's assume the relation is divide. What will be the order pairs of divides? 1 divides 1, 1 divides 2, 1 divides 4. Okay. The very first thing, if I ask you that what will be the least upper bound of 1 and 2. So my question is least upper bound of 1 and 2. That means an element which is on the upper side of 1 as well as on the upper side of 2, and that element should not be at the lower side of any other element which is on the upper side of 1 as well as on the upper side of 2. So do you realize that least upper bound of 1 and 2 will be what? So least upper bound of 1 and 2 will be 2. Least upper bound of 1 and 2 will be 2. Why? Sir, 1 divides 2. Therefore, 1 comma 2 belongs to divide, and 2 divides 2. Therefore, comma 2 belongs to 2 is on the upper side of 1 as well as on the upper side of 2. 2 is on the upper side of 1 as well as on the upper side of 2, and there is no other element which is on the upper side of 1 and 2, but at the same time at the lower side of 2, but at the same time at the lower side of this upper bound. So there is no such element, therefore least upper bound of 1 and 2 will be 2. I can understand that you may face some problem with respect to division. So let me explain with respect to less than equals to first so that you will be more clear. So let's assume let A is any set of real numbers. Let A is any set of real numbers, and A with respect to less than equals to the opposite. A less than equals to will be opposite. Obviously, we know that on any set of real number less than equals to a partial order relations, therefore this two will form opposite. For two elements, A and for two elements A comma B belonging to set A, in this case, what will be the least upper bound of A and B, and what will be the greatest lower bound of A? Sir, the relation you actually need to understand in terms of relation. The relation is less than equals to. So, you just need to understand that the maximum of this two, if I look at max of A and B, need example for everything. So let's say A is 1, 4, and with respect to less than equals to, talk about what will be so if I ask you that sir, what will be the upper bound of 2 and 3? So we are looking at the elements which are on the upper side of 2 as well as on the upper side of 3. So first of all, look for the elements which are upper side of 2. So 2 divides 2. So 2 is on the upper side of 2. Not divide, they less than 2 is less than equals to 2. Yes, 2 is less than equals to 3. Yes, so 2 is less than equals. So 2, 3 and 4, all three are on the upper side of 2. Clear? But we need an element which is on the upper side of both 2 as well as on 3. So 2 is not on the upper side of 3. Make sense? Now 3 is on the upper side of 3. as well as 4 is on the upper side of 3. So because 2 is not on the upper side of both 2 and 3, therefore 2 cannot be the upper bound of 2 and 3. 2 cannot be the upper bound of 2 and 3. But do you realize that both 3 and 4 are the upper bounds of 2 and 3, because both 3 and 4 are at the upper side of 2 and 3 with respect to relation less than equals to. So both of them are the upper bounds. So do you realize that 3 and 4 are upper bounds of 3 and 4? Sorry, are upper bounds of 2 and 3. 3 and 4 are the upper bounds of 2 and 3. But which among these two upper bounds of 2 and 3 is the least one? So it's not with respect to number. You only need to see that, sir, 3 is on the lower side of 4, but 4 is not on the lower side of 3. So among these two, 3 and 4, 3 is lower one and 4 is upper one. So the least one will be 3. So the least one will be 3. So do you realize that 3 and 4 are the upper bounds of 2 and 3, but the least upper bound of 2 and 3 will be equals to 3. Similarly, if you look at the greatest lower bound, so similarly, if you look at the greatest lower bound of 2 and 3, then what are the lower bounds of 2 and 3? Sir, 1 and 2 will be the lower bounds of 2 and 3. Why? Why? So you will eventually realize that 1 is on the lower side of 2 and 2 is on the lower side of 3. 1 is on the lower side of 3. 2 is on the lower side of 3. So both 1 and 2 are at the lower side of 2 and 3. Therefore, both 1 and 2 are the lower bounds of 2 and 3. But the greatest among these two is 2. Greatest among these two is 2. So if we look at greatest lower bound of 2 and 3, then this will be 2. If we look at least upper bound of 2 and 3, then it will be 3. So you simply realize that least upper bound for any two elements A and B with respect to less than equals to will be the maximum of A and B, and the greatest lower bound for two elements A and B with respect to less than equals to will be minimum of A and B. But is it the case that the least upper bound and greatest lower bound will always be minimum and maximum? Is it the case that least upper bound and greatest lower bound will always be minimum and maximum? No, sir. So let's try to understand another example. So let A is the set of all positive integers. Look at this. What am I saying? All positive integers. So for any set of positive integers, the relation divide will be a poset. Relation divide will be a poset. Now if I ask you for two elements, A comma B belonging to set A, what will be the least upper bound on? What will be the least upper bound of A and B, and what will be the greatest lower bound of A and B? Please think for a while. What will be the least upper bound of A and B? What will be the greatest lower bound of A and B? Sir, with respect to division, if we say x comma y belongs to relation divide, then it will only happen when y is divided by x, that is x divides y. So we are actually looking for an element which is divided by A as well as divided by B. We are looking for an element which is divided by A as well as it is divided by B, and it is the least one. So the element which is divided by A as well as divided by B is the least one, will be the least common multiple of A and B. So can I define it as LCM of A and B? Can I define it as LCM of A and B? Yes, sir. It is a set of all positive integers. So for any two positive integers, the LCM of those two positive integers will also be present in the set of all positive integers. Similarly, if we are looking at the greatest lower bound, then x is at the lower side. So we are looking for two elements which are on the lower side of A as well as on the lower side of B. So the element which divides A as well as B, the element which divides A as well as B will be the lower bound of A and B. Now we are looking for the greatest element which divides A as well as divides B, will be nothing but the greatest common divisor of A and B. So the element which divides A as well as B and is the largest one will be the greatest common divisor of A and B. Clear? So it's not necessary that the least upper bound and greatest lower bound will always be minimum maximum. It's not necessary that they will always be LCM or GCD. They may be anything. Let's assume if I define a new type of relation. So what do you mean by new type of relation? Let me explain. Okay. Let A is any finite set. Look at this carefully. Let A is any finite set and PA is the power set of set A. A is the power set of set A. Then the power set of set A with respect to relation subset or equal, it is not less than. So this relation is subset or equal. So please tell me, will it be a partial order relation? Please check whether subset or equals to one power set of A will be a partial order relation or not. Is the subset operation. So power set of A with respect to subset equals to the poset. Now please try to understand, every set is subset of itself, therefore it will be reflexive. Antisymmetric, a set with less number of element can be subset of a set with larger number of element, but vice versa is not possible. Therefore, if at all x comma y belongs to R, then y comma x cannot belongs to R until unless x is equals to y, that is reflexive. Again, if x is a subset of y and y is a subset of z, then x will be subset of z, so it will be transitive also. So this relation is reflexive, antisymmetric and transitive. Therefore, this will be a partial order relation on set power set of A. Therefore, these two together will form a poset. Now the question is, for two sets x comma y belonging to power set of A, if take two sets x and y belonging to power set of A. In power set of A, there will be number of sets and all of them will be subsets of set A. Then what will be the least upper bound of x and y? So sir, we are looking for a set. So if we say, let's assume if I say A comma B belong to subset or equals to, so it is only possible when B is superset of A. So if we are looking at the upper bound, then we are looking for a set which is superset of x as well as superset of y. We are looking for a set which is superset of x as well as superset of y, and it is the smallest one. So the smallest superset of x and y will be nothing but the union of x and y. Similarly, the greatest lower bound of x and y will be what? So the greatest lower bound of x and y will be. So we are looking at the lower side. So lower bound. So the greatest lower bound of A and B will be nothing but a set which is a subset of x as well as a subset of y, and it is the largest one. Sir, subset of x and y, which is the largest one, will be intersection of x and y. Will be intersection of x and y. So you just need to understand that as the relation changes, the definition of least upper bound and greatest lower bound will also change. With relation, definition of least upper bound and greatest lower bound will also change. Now, let me give you another example. Sir, is it necessary that least upper bound and greatest lower bound for every pair of element of set A will always exist? No, sir, it is not necessary. So let's look at the other example. Let, if I define 2, 3, 6, okay. Let A is this set, and for any set of positive integer, relation divide will be a partial order relation, the opposite. Now my question is, sir, what is the least upper bound of 2 and 3? What is the least upper bound of 2 and 3? Sir, least upper bound of 2 and 3 is 6. Yes, but if I ask you that, sir, what is the greatest lower bound of 2 and 3? Sir, please tell me the element which divides 2 as well as divides 3 and the greatest one. Sir, the element which can divide 2 as well as 3 is the element 1 only. But do we have element 1 in this set? No, sir. 1 is not present in this set. So can we say that does not exist? Sir, why? 1 is there? No, Baba. You just need to go and check the definition that for any two elements belonging to set A, their least upper bound should also belong to set A itself, and their greatest lower bound should also belong to set A itself. You are not looking at the number possible on the lower side, but that number should be in the set itself. Clear? So, if you look at this particular question, then you will think that, sir, there is an element which can be on the lower side of 2 as well as on the lower side of 3 with respect to relation divide, but that element is 1 and 1 is not present in this set. Therefore, in this poset, that is in the partial order relation divide, on this set, the least upper bound of 2 and 3 will be 6, but there is no greatest lower bound of 2 and 3 that exists in this set. So, the greatest lower bound of 2 and 3 does not exist. Similarly, if I look at the greatest lower bound of 12 and 18. So, is there any number which divides 12 as well as divide 18 and is the greatest one? So, the greatest lower bound of 12 and 18 will be 6, because 6 divides 12 and 6 divides 18. So, 6 divides both 12 and 18 and it is the greatest one. But the idea is, if you look at least upper bound of 12 and 18, then is there any number which is divided by 12 as well as divided by 18 and is present in this set A? No, sir, there is no number which is divided by 12 as well as divided by 18 and present in this set. So, greatest least upper bound of 12 and 18 does not exist. And the greatest lower bound of 12 and 18 will be actually 6. Greatest lower bound of 12 and 18 will be 6 in this. So, it may be possible that the least upper bound exists for some pair of element but does not exist for another. Similarly, greatest lower bound exists for some pair of element and does not exist for some other pair of element. So, it's fine. So, please try to understand what in a poset, least upper bound and or greatest lower bound need not exist for every pair of element. So, it's not necessary that least upper bound or greatest lower bound will exist for every pair of element. But if it exists for n pair of element, it exists for any pair of element, then it is unique. So, it cannot be the case that for a pair of element A and B, there are 2 or more than 2 least upper bounds. Similarly, it is not possible that for a pair of element A and B, there are 2 or more greatest lower bound. Yeah. So, if you fall in a situation that there are 2 such sets which are on the upper side, then we will eventually say that there is no least upper bound and there is no least upper bound, or there is no greatest lower bound for that particular pair of element. There cannot be 2 or more upper bound and or greatest lower bound for a pair of element. Please. Okay, so I hope we have understood the concept of least upper bound and greatest lower bound. Now we will start with the discussion of Hasse diagram, and we will try to visualize the least upper bound and greatest lower bound in the Hasse diagram. Okay, sir. So, what is a Hasse diagram? Basically, Hasse diagrams are constructed for poset. Therefore, they are also known as poset diagram. In a Hasse diagram of a poset, sir, what do we know? So, if it is a poset, then it will be a partial order relation. So, the relation will be reflexive, the relation will be transitive. And apart from that, the relation will be antisymmetric. So, please understand that we always know that reflexivity and transitivity will be present in a partial order relation. Therefore, these two things are not explicitly represented in a poset diagram. They are implied that if you are constructing a Hasse diagram, it is actually for a poset. It is actually for a poset, and we know that the poset will be reflexive and transitive. Therefore, we don't need to represent the edges in the poset diagram with respect to reflexivity and transitivity. I'll explain it in. Don't worry. So, what happens in a poset? What happens in a poset diagram or in a Hasse diagram? So, if I say any set A equals to 1, 2, if I say that doesn't equals to, then we know that this will be a poset. This will be a poset. A with respect to relation less than equals to will be a poset. Now, for all the elements of the set, there will be a vertex in the Hasse diagram. So, there is a vertex corresponding to every element of the set. For every element of the set, there will be a vertex in the Hasse diagram. So, nothing but Hasse diagram will have collection of vertices and edges. Now, next thing. Sir, okay, that for every vertex, for every element there will be a vertex. But when exactly there will be an edge between two vertices? When exactly there will be an edge between two vertices? So, do you realize that one relates to two? So, one relates to one as well as one relates to this relation less than equal. So, one relates to two. So, if one relates to two, then we will try to create an edge between 1 and 2, provided there should not be any element x such that 1 relates to x and x relates to 1 relates to x and x relates to 2. Because if 1 relates to x and x relates to 2, then 1 relates to 2 because of transitivity. 1 relates to 2 because of transitivity. So that's what you need to understand. But what will happen? Sir, there is an edge from vertex A to vertex B. There is an edge from vertex A to vertex B only if A is this one. Only if A relates to A relates to, that means A comma B is present. Only if A relates to B and there is no element X in the set such that A relates to X and X relates to B. So there should not be any element X such that A relates to X and X relates to B. So what happens? Sir, if 1 relates to X and X relates to 2, then by transitivity 1 will relate with 2. Then by transitivity 1 will relate to 2. So because 1 relates to x, therefore we will draw an edge between 1 and x, and because x relates to 2, we will draw an edge between x and 2. So we don't need to draw an explicit edge between 1 and 2 because we know that 1 and 2 are related via this vertex edge, via this vertex x. Clear? So that's the idea, that what will happen in the Hasse diagram. There's an edge from vertex A to B if and only if A relates to B, A must relate with B, but there should not be any element X, such that A relates to X and X relates to B. Because if it happens, then the relation between A and B will be because of transitivity. So that's what we say, that transitivity is implied in the Hasse diagram, not represented explicitly. We already know that we are constructing a Hasse diagram for our poset, so it will be transitive. We don't need to represent the transitivity explicitly in the Hasse diagram. It is already implied. It is already implied. Clearly, another thing is, sir, when we talk about a poset, we know that 1 comma 1 will definitely belong to relation. Why? Because relation is a reflexive relation. So we know that 1 relates to 1. We know that 1 relates to 1. So if 1 relates to 1, then if we have a vertex 1, and because 1 relates to 1 and there is no other element x such that 1 relates to x and x relates to 1, then we will try to draw a self loop. Then we will try to draw a self loop at vertex 1 if we try to represent reflexivity explicitly in the Hasse diagram. But we will not draw such self loops in the Hasse diagram. Reason is quite simple, that in the Hasse diagram we do not represent the reflexivity explicitly. It is implied in the Hasse diagram. So let's see next thing. No self loop on the vertices. No self loop on the vertices. That is, reflexivity is implied in the Hasse diagram. We don't need to represent it explicitly. Now, the last thing that you need to understand is that, sir, if A relates to B, if A relates to B, then we are actually thinking that there is an A, there is a B, there is an A. We are trying to relate A and B. But if there is an edge between A and B, then how do we identify whether A relates to B or B relates to A? Whether A relates to B or B relates to A. So there are two ways of doing this. Sir, if you want to represent that A relates to B, then you can draw an edge from A to, so you can draw a directed edge from A to B, that is A relates to B. If you want to represent that B relates to A, if you want to represent that B relates to A, so this is with respect to this. If you want to represent that B relates to A, then you can have two vertices. One is with respect to B, another is with respect to A, and you can draw an edge, directed edge from B to A. But this is when you are using concept of directed edges. That is, when you are trying to make the Hasse diagram as a directed graph. But please try to understand, there are different authors. Some of them may represent the Hasse diagram using the directed edges, and some of them may not use the concept of directed edge. So I will also, while I'll explaining the concept, I'll not use the concept of direction, but we use upward orientation. What do you mean, sir? It is not directed. Generally, the Hasse diagrams will not be directed. Generally, the Hasse diagrams will not be directed, but it uses implied upward orientation. What do you mean when I say it uses implied upward orientation? That is, if A relates to B, then A be at the lower side the diagram, and B has. What does it mean? Lower side, higher side? Not clear. So basically, if we have A relates to B, then it implies, then if we construct an Hasse diagram, A will be at the lower side and B will be at the higher side in the diagram. So rather than drawing an direction from A to B, we'll keep A at the lower side and we'll keep B at the higher side in the Hasse diagram. Yeah, so that's just the notation. Sir, what if A and B are not related? If two elements are not related, if two elements are not related, then they may be at the same level. They may be, need not be, but they may be. Hold on. Two elements are not related. Two elements are not related. Then at okay. Anyway, this will be very much clear once I try to construct the hash diagram for all these examples. Okay. So this is what we are trying to do. Anyway, sir, you may be thinking that, sir, what is this D6? So try to understand. If n is any positive integer, n is any positive integer, then Dn represent the set of all positive divisors of n. Dn represents the set of all positive divisors of n. We are using 2 here, d6, d12. So let me explain that. d6 will be nothing but the set of all positive divisors of 6. So 1 divides 6, 2 divides 6, 3 divides 6, and 6 divides 6. So is there any number, any other number, any other positive number which divides 6? No, sir. When we talk about d12, sir, what are the positive divisors of 12? So 1 divides 12, 2 divides 12, 3 divides 12, 4 divides 12, 6 divides 12, 12 divides. Similarly, if I try to represent D18, so what will be D18? So 1 divides 18, 2 divides 18, 3 divides 18, divides 18, 9 divides 18, 18 divides. So that way, you can define Dn for any positive integer, and Dn is nothing but the set of all positive divisors of that number n. Anyway, so let's try to construct the hash diagram for all of them. So what did we say? So in the hash diagram, there will be a vertex corresponding to every element of the set. So let's begin. So first of all, let's start with the -1. Let's begin with any element. Start with -1. So does -1 relates with -1? Yes, sir, -1 relates with -1. Is there any element between -1 and -1 such that -1 relates to, or I would rather say, -1 is less than equals to x and x is less than equals to -1? Do we have any such element in this set? No, sir, there's no other element apart from x itself. So you will actually, apart from -1 itself, so there is no other element such that -1 relates to x and x relates to -1. Therefore, you will try to draw an edge from -1 to -1. But as we said that there will be no self loop in the hash diagram. Therefore, you will not draw any edge with respect to -1 relates to -1. Then, sir, does -1 relates with 0? Yes, sir, -1 relates with 0 because -1 is less than equals to 0. Now, do we have any element x such that -1 is less than equals to x and x is less than equals to 0 apart from -1 and 0? No, sir, we do not have any other element apart from -1 and 0. Therefore, we will draw an edge between -1 and 0. Sir, -1 relates with 0. 0 does not relate with -1. -1 relates with 0, right? Because we have a situation that -1 comma 0, -1 comma 0 belongs to less than equals to 0 comma -1 does not belong to less than equals to. So -1 relates to 0. Therefore, -1 will be at the lower side and 0 will be at the upper side. It is upward inclination. So either you can do this, or you can use the concept of direction if you want. But even if you don't do this, then also it's absolutely fine, because by default in the hash diagram we will use upward orientation. Okay, sir. Now -1 relates with 0. Does -1 relates with 2.5? Yes, sir, -1 relates with 2.5. But there exists an element 0 such that -1 is less than 0 and 0 is less than 2.5. Therefore, we don't need to draw an edge between -1 and 2.5, because we only draw an edge between a and b if there is no such element x such that a relates to x and x relates to b. If there exists any such element x, then we do not draw an edge between a and b, because we know that -1 relates to 0 and 0 will ultimately relate with 2.5. So we know that -1 to 2.5 are related via 0. We don't need to draw an explicit edge between -1 and 0. That's the idea. The transitivity is implied in the hash diagram. We do not represent it explicitly. Make sense? So -1 and 0 is perfectly fine. I'll explain that in a while. So -1 relates to 0 is okay. -1 relates to 2.5, but there exists an element 0, therefore we will not use this. -1 relates to 4 also, but there are 0 and 2.5 such that -1 relates to 0 and 0 relates to 4. Therefore, no direct edge between -1 and 4. Same for 6. So done, sir. We are done with respect to -1. Let's move to the next element of the set, that is 0. Now, 0 does not relate with -1. Forget about that. 0 relates with 0, but no self-proof. 0 relates to 2.5. So 0 is less than 2.5, and there is no element x such that 0 relates to x and x relates to 2.5. Therefore, we'll draw a direct edge between 0 and 2.5. Similarly, 0 relates to 4, but there is 2.5. 0 relates to 6, but there is 2.5. Therefore, we will not draw any edge from 0 to 4 or 2.4 or 6. Next is 2.5. Sir, 2.5 does not relate with -1. 2.5 does not relate with 0. 2.5 relate with 0. Sorry, 2.5 relate with 2.5. But there will be no loop. Apart from that, 2.5 relates with 4, and there is no such element such that 2.5 relates with x and x relates to 4. Therefore, there will be a direct edge between 2.5 and 4. Now, 2.5 relates with 6, but there is an element 4. Therefore, there will be no direct edge from 2.5 to 6. Done. Next one is 4. Sir, 4 relates with 6. 4 relates with 6. So, this is your Hasse diagram. This is your Hasse diagram for this given poset. Clear? Now, please try to understand. Sir, this Hasse diagram looks like a linear chain. This Hasse diagram looks like a linear chain. Come on, one more important thing which you need to understand is that for any set of real numbers, relations sub less than equals to will be a total order relation. So it is a totally ordered set. Yes or no? It is a poset as well as a toset. It is a totally ordered set. Yes, sir. It is a totally ordered set. Now, important thing which you need to understand is that for any totally ordered set, the Hasse diagram will look like a linear chain, right? So, for any totally ordered set, Hasse diagram will look like a linear chain. Therefore, totally ordered set are also known as linearly ordered set. Are also known as linearly ordered set. It's fine. Sir, let's move to the next diagram. Let's move to the next poseted diagram. Now, what is this d6 with respect to divide? So, forget about that. What is d6? Sir, d6 is actually nothing. d6 is actually nothing but 1, 2, 3, 6 with respect to relation divide. Now, try to draw the poset diagram. Sir, we start with 1. 1. 1 divides 1 but no self loop. 1 divides 2, yes sir, 1 divides 2, and there is no other element. There is no other element such that 1 divides x and x divides 2. Okay, sir, why did you draw this like that? That why this is a slant line? It does not matter. It does not matter. If I start with 1 and if I draw 2 here, it's also absolutely fine. Don't worry about that. But I know that what type of diagram will be created, therefore it's just my habit. So don't worry about that. Sir, 1 divides 2. Fine. Does 1 divide 3? Yes, sir. 1 also divides 3. Do we have any element x such that 1 divides x and x divides 3? No, sir. 1 divides 2, but 2 does not divide 3. And there is no other element x such that 1 divides x and x divides 3. Therefore, there will be a direct edge between 1 and 3 as well. There will be a direct edge between 1 and 3 as well. Okay. 1 divides 2 as well as 1 divides 3. Now the idea is, why these two elements are on the same level? 2 and 3 are not related with respect to divide. Neither 2 divides 3 nor 3 divides 2. So if the elements are not comparable, If two elements are not comparable or not related, then they may be at the level. Then they may be at the same level. Yeah? Yes, sir. So they may be at the same level. Now, forget about this. Does 1 divide 6? Yes, sir, 1 divides 6. But there are elements such that 1 divides x and x divides 6. 1 divides 2, fine. 2 divides 6, fine. So there will be no direct edge. There will be no direct edge between 1 and 6. No, sir, we will not draw any such edge because 1 divides 2, 2 and 2 divides 6. So we know that 1 and 6 will be related transitively. Okay, so we are done with 1. We are done with 1. Let's move to the next element of the poset, that is 2. Does 2 divide 1? No, sir. 2 divides 2 but no self proof. 2 divides 3? No, sir. 2 divides 6? Yes, sir. 2 divides 6. Do we have any element between 2 and 6 such that 2 divides x and x divides 6? No, sir. There is an element 3 but 2 does not divide 3. Therefore, there will be a direct edge between 2 and 6. There will be a direct edge between 2 and 6. Similarly, you can draw this, that there will be a direct edge between 2 and 6. Okay. Anything else? No, sir. The final will be, sir, next element will be 3. Does 3 divide 6? Yes, sir, 3 divides 6. Do we have any element between 3 and 6? No, sir. So, there will be a direct edge from 3 to 6 as well. There will be a direct edge from 3 to 6 as well. So, both of them are same. Don't worry, they may be looking different, but the properties which are represented by this particular poset diagram and this particular poset diagram are exactly same. Don't worry. Clear? So, this is your poset diagram for this particular poset. Sir, next one, D12. Next one is D12. Sir, what is D12? So, D12, 1, 2, 3, 4, 6, 12. So, we are actually looking for one poset diagram of 1, 2, 3, 4, 6, 12. With respect to divide. Sir, draw this. I'll be quick. Sir, 1 divides 2, 1 divides 3. Okay. For every other element, 2 and 3 exist. Now, 2 divides 4. Okay. 2 divides 6. So, for 12, 4 and 6 exist. So, 3 divides 6. Okay. And 4 and 6 divides 12. So, this will be the poset diagram for this particular. Clear? Sir, again, 1 divides 2. Yes, sir. 1 divides 3. Yes, sir. 1 divides 4. Yes, but there is 2 such that 1 divides 2 and 2 divides 4. Though no direct edge between 1 and 4. They are connected transitively via 2. Similarly, 1 divides 6, but 2 and 3 exist such that 1 divides 2, 2 divides 6, 1 divides 3 and 3 divides 6. So, 1 and 6 are connected transitively. You don't need to draw them explicitly. You don't need to draw them explicitly. This is your poset diagram. Next, sir, we always start with one element and reach to the top. We start with one element, reach to the top. Is it always the case? No, Baba, it's not the case. Let's look at this particular thing. Now, this is 2. Does 2 divide 3? This 2. Does 2 divide 3? No, sir. Does 2 divide 4? Yes, sir. So, 2 divides 4. Cool. Good enough. Does 2 divide 6? Yes, sir. 2 divides 6. Done with 2? Okay. Let's move with 3. Sir, does 3 divide 2? No, sir. Does 3 divide 4? No, sir. Does 3 divide 6? Yes, sir. So, please, 2 and 3 are not related. Sir, 2 and 3 are not related. So, they may be at the same level. 2 and 3 are not related. They may be at the same level and 3 divides 6. So, that's the only poset diagram for this given poset. Clear? Okay. Next. Sir, 2, 3, 6, 12. If I try to draw for this, so this is 2. 2 divides 6. 6, 2 divides 12. Forget about that. So 3 divides 6. And 6 divides 12. So this will be the poset diagram for 2, 3, 6, 12. With respect to relation divides. Here. Next. Sir, can you please draw the poset diagram for this? Yes, sir. So this is your 1. 1 divides 2. Okay. 1 divides 3. Okay. 1 divides 4, 6, but there exists other elements. 2 divides 4, yes. 2 divides 6, yes. 2 divides 4, 2 divides 6, nothing else. 3 divides 4, no, sir. 3 divides 6, yes, sir. Does 3 divides 9? Yes, sir. 3 divides 9, and there is no other element, therefore, this will be divides. Does 4 divide 6? No, so no relation. 4 divides 9? No, so no relation. 6 divide 9? No, so they may be at the same level. They may be at the, So this is the poster diagram. Now come on, let's go back and try to understand certain things. Sir, we were just discussing the concept of least upper bound and greatest lower bound. We are just discussing the concept of least upper bound and greatest lower bound. If somebody asks you that, sir, what is the least upper bound of 2 and 3? So what did I say? Least upper bound. So we are going at the upward direction. We are going at the upward direction. So the element at which 2 and 3 join at the upper side will be called least upper bound of 2 and 3. Sir, now your question may be, sir, 2 and 3 join at 12 also? Yes, sir. But 2 and 3 are joining each other at 6 and 12. But the lowest level, 2 and 3 join each other at the upper side at 6. So we are looking at the lowest of all the upper bound. Therefore, least of 2, 3 will be. Similarly, if I ask you for the greatest lower bound, so where exactly 2 and 3 meet each other at the lower side? So 2 and 3 meet each other at the lower side at 1. Therefore, the greatest lower bound of 2 and 3 will be equals to, greatest lower bound of 2 and 3 will be equals to 1. Sir, what if it is a totally ordered set? What if it is a totally ordered set? So, if we have element 4 and if we have element 0, so where exactly 0 and 4 meet each other at the upper side? So where exactly 0 and 4 meet each other at the upper side? 4 will stay there itself and 0 will reach to 4. Therefore, 4 and 0 will meet each other at element 4. Therefore, the least upper bound of 0 and 4 will be 4. Similarly, where exactly 0 and 4 meet each other at the lower side. So, 4 will go down up to 0 and 4 and 0 will meet each other at 0 itself. Therefore, the greatest lower bound of 4 and 0 will be 0. So, the least upper bound of 4 and 0 will be 4. The greatest lower bound of 4 and 0 will be 0. So on a line, please try to understand. On a line, the element at the upper side will be the least upper bound of those two elements and the element at the lower side will be the greatest lower bound of those two elements. Otherwise, the element at which two elements join each other, sir, that's why we say least upper bound is join. Least upper bound is join. The element at which 2 and 3 join each other at the upper side is least upper bound of 2 and 3. The element at which 2 and 3 meet each other at the lower side, greatest lower bound is meet each other at the lower side is called greatest lower bound. Clear? Now, for any random diagram, if I look at, so what is the greatest lower bound of 4 and 3? So the greatest lower bound of 4 and 3, where exactly they meet each other at the lower side. So 4 and 3 meet each other at the element 1. Therefore, the greatest lower bound of 4 and 3 is actually nothing but 1. Now my question is, sir, where exactly 6 and 9 join each other? Sir, least upper bound of 6 and 9. Is there any element in this poset at which 6 and 9 join each other at the upper side? So there is no element at which 6 and 9 join each other at the upper side. So least upper bound and 6 and 9 does not exist. Does not exist. Okay. Apart from that, sir. Last thing. Sir, there's the elements which are at the lowest level in the poset diagram. The elements which are at the lowest level in the poset diagram are known as maximal element. Sorry, minimal. The elements at the lower side, lowest level, the elements at the lowest level in the poset diagram are known as minimal element, and the elements at the uppermost side of the poset diagram are known as maximal element. See, the definition is quite clear that if there is no other element apart from itself which is at the upper side of that element, then that will be called a maximal element. So do we have any element in this poset which is on the upper side of 6 apart from 6 itself? No sir, therefore 6 is maximal. So when do we say that element is a minimal element? If there is no element which is at the lower side of a given element, then that element will be called minimal element. So there is no other element apart from -1 which is at the lower side of -1. Therefore, -1 is the minimal element. Okay, in a while I'll explain. So this is maximal. This is minimal. So this is a maximal. Sir, both of them are at the topmost position of the poset diagram. Therefore, two maximal. Two minimal. What about that? Sir, maximal, but two minimal. Sir, three maximal. One minimal. So I just told you the definition of minimal and maximal. That minimal is nothing but an element corresponding to which there is no other element in the poset which is at the lower side of that element will be called minimal. So with respect to 1, there is no other element in the set which divides 1 apart from 1 itself. Therefore, 1 is minimal. There is no other element in this poset which is divided by 12 or divided by 6 or divided by 9. Therefore, there is no element at the upper side of 4, no element at the upper side of 6, no element at the upper side of 9. Therefore, 4, 6 and 9 are the maximal elements. Please, as I told you, if there exists 2 or more maximal elements, then the least upper bound will not exist for them. If I'll the slide, so both of them can be there. So we go there. So the least upper bound does not exist. Sir, where exactly these two elements 2 and 3 meet each other? Sir, no element. So the greatest lower bound of 2 and 3 does not exist. So in our poset, what is actually happening? If there exist 2 or more maximal elements, if there exist 2 or more maximal elements, then least upper bound does not exist for any pair of two distinct elements. For any pair of two distinct maximal elements. Clear? Similarly, if there exist two or more minimal elements, or more minimal elements, then greatest lower bound does not exist for any pair of two distinct elements. You can take any pair. Let's say if there are two or more. So the least upper bound of 4 and 6 does not exist. The least upper bound of 4 and 9 does not exist. The least upper bound of 6 and 9 does not exist. Clear? So if you take any pair of two distinct maximals, the least upper bound will not exist. If you take any pair of two distinct minimals, the greatest lower bound will not exist. Please, I have explained the definition of maximal and minimal element. I would also like to explain the definition of minimum and maximum element. So the element which is at the upper side of all other elements of the poset will be called maximum element. Look at this, sir. Is 6 at the upper side of all other elements? Yes, sir. 6 is at the upper side of -1. 6 is at the upper side of 0. 6 is at the upper side of 2.5. 2.5. 6 is at the upper side of 4. 6 is at the upper side of 6 itself. Right? So the element which is at the upper side of all the elements is called a maximum element. So it is maximal plus maximum. Clear? Now the element which is at the lower side of all other elements, all the other elements of the poset will be called minimum. So it is minimal plus minimum. Clear? This is maximal plus maximum. This is minimal plus minimum. You can actually see, sir, why are you saying, sir, 6 is divided by 1, 6 is divided by 2, 6 is divided by 3, 6 is divided by 6. That is 6 is at the upper side of all other elements. 1 divides 2, 1 divides 3, 1 divides 6, 1 divides 1. 1 is at the lower side of all the other elements. Therefore, it is minimum. Clear? Similarly, look at this. Sir, 1 divides 2, 1 divides 3, 1 divides 4, 1 divides 6, 1 divides 12. Therefore, 1 is minimum. So, which is at the lower side of all the elements of the poset will be minimum. The element which is at the upper side, sir, 1 divides 12, 2 divides 12, 3 divides 12, 4 divides 12, 6 divides 12, 2 divides 12, and 12 divides 12. So the element which is at the upper side of all other element will be maximum element. Okay. So please try to understand. If there is a unique minimal, then it will also be minimum. If there is a unique maximal, it will also be maximum. Ho 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 ho. Sir, unique maximal, so it is also maximum. Unique minimal, it is also minimum. Unique maximal, it is also maximum. Unique minimal, it is also minimum. Unique maximal, it is also maximum. Unique minimal, it is also minimum. Here, sir, two maximal. Do we have any element which is at the upper side of all other elements? Sir, there is no element which is divided by all the elements of this set. Sir, 2 does not divide 3. So let's look at this. Sir, do we have, look at, try to understand, I don't know whether you are getting it or not. Is there any element x which is at the upper side of 2, 3, 4, 6 in this set? No, sir, there is no such x such that is divided by 2, 3, 4 and 6, all of this set. No such element exists. Therefore, there is no maximum element. So, if there exists two or more maximal elements, there will be no minimum element. If there exists two or more maximal element, then there will be no maximum element. If there exists two or more minimal elements, there will be no minimum element. So if you want, you can understand that. Next slide, next, be clear. Sir, unique maximal, so it will also be maximum. Why? So it will be divided by all other element of the poset. You can check. Sir, 2 divides 12, 3 divides 12, 6 divides 12, 12 divides 12. But if you have two minimal, then there will be no minimum element. There is no element which divides all the elements of this set. So 2 divides 2, 2 divides 6, 2 divides 12, but 2 does not divide 3. Therefore, 2 is not at the lower side of all the elements. So 2 minimal. These are 2 minimal. So if 2 minimal, therefore no minimum. If you have 2 maximal, therefore no maximum. Two minimal, therefore no minimum. So if you have a unique maximal element, then that will also be the maximum element. If you have a unique minimal element, it will also be the minimum element. If you have two maximal, there will be no maximum element. If there exists two or more minimal, then there will be no minimum element. This minimal and maximal element of are also known as least and greatest element in the poset. So anyway, look at this here. P maximal, therefore no maximum. But do you realize that 1 divides all other elements? Therefore, this is also the minimum. Plus then. So, we have seen the concept of least upper bound and greatest lower bound in our poset. We have also understood the concept of Hasse diagram. What actually happens in the Hasse diagram? So, there will be a vertex corresponding to every element of the set. The edge will be present between two elements A and B, and only if A relates to B and there exists no element X such that A relates to, if there exists no element X such that A relates to X and X relates to, so there should not be any such X. If there exists any such X, then we will have A to X and X to B, but we will not have any edge between A and B. That's another idea. Now, that is transitivity is implied. It is not represented explicitly. There will be no self loop and it will use upward inclination. So, at some places you may see directed Hasse diagram, but there is no difference between directed Hasse diagram and in a non-directed Hasse diagram. It's just that the upward inclination will show that how exactly the elements are related. So, one at the lower side and 3 at the upper side, then one relates with. Now you see 6 and 9 at the same level. That means neither 6 relates with 9, nor 9 relates with 6. Okay? So these are some basic concepts. Now let's try to understand. Have you understood the concept of least upper bound, greatest lower bound? So the elements which are at the upper side of A and B, and there is no other element which is at the upper side of A and B, but at the lower side of C, then C will become the least upper bound. So there exists an element C at the lower side of A and B such that there exists no element D which is at the lower side of A and B and at the upper side of C, then C will become greatest lower bound. Hasse diagram, I have explained minimal and maximal element. So minimal element will be the element, an element will be minimal element if there is no element which is at the lower side of that given element A. Okay. An element A will be the maximum element if there is no element which is at the upper side of element A except A itself. So these are minimal and maximal element. Now least element or minimum element or greatest element or maximum element. So if there exists two or more minimal, there will be no minimum. If there exists two or more maximal, there will be no maximum. If there exists a unique minimal, then it will also be the minimum or least element of the poset. If there exists a unique maximal, it will also be the maximum or greatest element of the poset. So that will be all related to least upper bound and greatest lower bound of the poset. Hasse diagram, the representation of least upper bound and greatest lower bound in the Hasse diagram, and minimal element in the poset, maximal elements in the poset, and minimum and maximum, that is least and greatest element of the poset. So we have covered everything. Tomorrow we'll try to understand, from next class onward, we'll try to understand the concept of lattice. Okay, so that will be interesting to see that what is our lattice and what are the different types of lattices. The question can be framed on that particular concept. But for today's session, that will be all. Thank you very much for joining. Take care, keep learning. Have a nice day.